Okay, the third part of this theory is to look at transient response. Basically, we're going to apply a sine wave moment similar to what we did in the harmonic response, but in this case we just apply starting from transient stage, then we hopefully can see that gradually come into a steady state. Okay, so to do that, you want to add another analysis, which is this transient structural. So you just add that. So you see there's another module being created. Again, it's being created in the workspace as well. So again, you have to redefine your boundary conditions. And then redefine the moment that you want to apply. So in this case, the moment that we apply is slightly different to what we did before. Because this one, you cannot just give a magnitude because it will be constant if you just give a magnitude. So what you really want is give a time function, the torque about y direction. So you can go here and you can define your torque as a function. Then you can write this function equals 250, this is our magnitude, times sine wave or cos wave. And in answers, the cos and sines, the values given in degrees. Remember, it's not in radians. So in this case, we want to apply for that 0.96 hertz, but that should times 360 rather than 2 pi because that's in the unit of degrees. Okay, so you and then that times the time variable. Okay. Alright, so that's it. But by default, the simulation only covers 1 second, which is obviously not good enough. So we just want to extend that. Just go into Analyze Settings. Then you want the end time to be 20 seconds, for example. So we have 0.9, around 1 hertz and 20 seconds, so about 20 cycles. Okay. So this very important thing is to set up the time step, because the time step affects how accurate your result is, especially if you have a very fast response dynamic systems. But having too fine time steps, you're going to end up with a lot longer simulation time, so you have to find a balance between that. So in this case, we will just use 0.05 seconds as a constant. So maximum and minimum are both 0.05. Okay. Another thing, in the transient stage, if you imagine if you apply the force, you have to set up a damping ratio. Otherwise, you will never get into a steady state because the transient state will take infinite number. It will take infinite time. So we just have to add dampings in here. So they've got damping control still under the analyst settings. So in this case, we want a damping vs frequency option. So we want to set the damping at 1 hertz, and we just put a very small damping ratio of 0.03. Just to get a better comparison with our harmonic response. Okay, and that's it. That's our settings. Then we need to define what we need to get. Again, firstly, total deformation to give you the shape, and then because last time we were looking at this corner point here, so we want to just look at the same point to see if we got the same results. So we got directional deformation, and remember we were looking at the direction in Z direction, and you want to put only look at this point. So the geometry selection, you want to just apply to one point here. Okay, so that just gives you the directional displacement of that point at that forcing frequency. All right, that looks all good. We can run it. It takes a bit longer than the previous case, but our model is simple enough. It shouldn't take too long. Okay, it took about a bit less than 1 minute to run it, and now we have the results. So this is a total deflection. If we can have a look, so you can see start with not too much and slowly build up and gradually get into a steady stage, which is the amplitude become stabilized. So if we can exaggerate that a little bit, so that just get into a steady state. Okay, so that's for the total deflection or the animations. But if we look at that point, so that's the displacement of that particular point we picked, and it's gradually growing up to about plus minus 2.1 meters. And in comparison, in our harmonic response, we're getting an amplitude of a 4, so that's very close. Yeah, so that's the transient response. So we're getting into a transient response, then gradually getting to a steady state response. Remember, there's a damping ratio affecting the results, affecting the steady state results by large amounts as well, because this is close to a resonance case. Okay, so that's all covered in this series. So we got an example structure, and we did a model analysis to give natural frequencies and mode shapes. Then we done a harmonic response analysis to give you a steady state response of the system with a given forcing frequency or forcing frequency range. Then we get into a transient stage to get a transient response as well as a steady state response. Okay, so that concludes this series. Thank you very much.